And I think the next part of the presentation, which is about the open source implementation of a simple shutter system, is a fantastic about what kind of tools can be part of this. This is a great tool that's, I think, reasonably easy to implement in many parts of the world. And so we have Mathias Fischer joining us. Thank you very much for making yourself available to tell us a little about the development that you've done and how you've shared it and how it could be useful for the community.
Of course, thank you, and thank you for having me today. I'm gonna share my screen. Thank you very much. My name is Mathias Fischer. I'm an undergraduate student at NC State, and I just wanted to show you guys about cost-effective open source light shutters. Firstly, I'm gonna show a video just so you can see the shutter in action and see the scope of the project. So as you can see, it's a pretty simple setup. The thing is, most people buy a shutter, but the problem is the commercial shutters can be up to $1,000. So our main goal was just to find a cost-effective and cheaper alternative to commercial shutters. All right, there. So here are the system components that we used. Firstly, I'm going to talk about the shutters themselves. Then I'll move on to the heart of the system, the microcontroller, which we use Arduino. I'm also going to talk about some servo shields, which we needed to drive the shutters. And then local control through the display. We had two different types of display shields. And then finally, I'll talk about communication, remote communication from USB or digital inputs. So there's two types of actuators that we used. The first one that we use is RC servos. And servos use a rotary motion, which we use to block or let the beam pass. And servo positions are determined by the duty cycle pulse width modulation. You can see here the little diagram of it. And you can see there's different iterations, different positions based on the actual pulse. And a typical pulse, or the standard frequency is 50 Hertz, so 20 milliseconds. And each servo was around $5, so much cheaper than a commercial shutter. And we also needed to mount them to posts, so we designed 3D models and printed them in plastic. But for the actual blades themselves, we of course don't want the blade to melt from a laser beam, so we cut aluminum and basically just screwed it on. And there's two different types. You hear the horizontal servo, or it's the same servo, but positioned horizontally and then positioned vertically here. And it just depends on what you need for your experiment, what is better. The other type of actuator that we tried was solenoids. And of solenoids themselves, there's two types. There's a linear motion solenoid, which uses the plunger to push and pull the blade. We oriented it so when we pull, the beam is passed. When we push, it's blocked. And the second type of solenoid is a rotary solenoid. So it uses also rotational motion to block or pass the beam. And solenoids are different from servos because they use a continuous current to pull it open. And on the way back, it's spring-loaded. So when current is taken away, it will just spring forward and block the beam. The negative about this is that the motion is very jarring because of the spring-loadedness, and it causes vibration and can cause a lot of noise, which, depending on your experiment, if it's sensitive, it may mess up your experiment. And one other thing is that the spring causes an internal failsafe, which when power is not applied, it'll close. And this is not the same on the servo. So the servo will just stay in the same position. If power is taken away, the solenoid will block the beam. So for our microcontroller, we chose Arduino Uno. because it's widely available and it's popular and there's a lot of online sources for it. They're also pretty customizable when you're programming it, which is definitely a plus. There's also many shields that we used, so I'll talk about 2 of them later. And yeah, the USB connection is very standard, which is also great for the Arduino. It's around $25. And we did find some challenges, which is the limited amount of timers for pulse width modulation, which again is used by the servos. So if you have 1 or 2 servos, it's usually okay connected to the Arduino. If you get 3, 4, or more servos, they all have to use the same timer. So you'll find a jitter on the servos, which also can affect an experiment. Also for the power, it might not draw enough current if you have multiple shutters. It just might not be strong enough, it might not work. And for solenoids, not even one solenoid will work. So you'll need a different way to power it to drive the shutters, which we chose shields. So we have 1 servo shield and 1 motor shield, which are these for the solenoids. I'll talk about the servo shield first. It has up to 16 channels, which means you can have up to 16 servos connected at one time. It also uses external power supply. It doesn't technically need to, but we did. And the shield handles the pulse width modulation timing separately, so we don't have to draw from the Arduino. And this eliminates the jitter that might mess up an experiment, and it's just very stable. And it uses I2C communication, which is also very standard for this type of communication. They're both around $20, by the way. For the motor shield, it only has up to 4 channels, so only 4 solenoids can be powered at the same time, driven. This one requires an external power supply, unlike the servo shield, which you can choose not to use it. This one, the motor shield, needs it. And it also uses I2C communication, which is very standard, and it's around $20. The last shield I'll be talking about is the display shields. The first one is LCD display with buttons. I'll show a video here. As you can see, it's only 1 line display, which is a little bit unfortunate, but we can just cycle through different devices if we have multiple shutters with the buttons, and also you choose the position, so open or closed with the buttons as well. This one's around $20. Here you can see the touchscreen display. It's also LCD TFT for touchscreen. I'll show a video. And if you notice at the end, you can see the solenoid failsafe. And the display is a little bit different on this one. You can't actually see it in the video, but we have it up to 4 devices shown at a time, which can be nice that you don't have to cycle through each one. But at the same time, if you have more than 4 devices, you'll need to integrate a way to cycle through or scroll to access other devices. This one's a little bit more expensive too. Since we talked about the local control, which the display is the local control, we were talking about the remote control as well. So the way to get from the computer to the Arduino is using ASCII commands through serial port, and this just happens via the USB connection. And ASCII commands just control a couple of different things like configuration, status requests, controlling the actual shutter, and I'll talk about some of them a little bit later. We also have electrical lines. So we had the digital input, which can control shutter state, either on or off, and we just had 0 volts being off and 3 to 5 volts being on. They use BNC connectors, which are also very standard. And they can actually be mapped to multiple different ones. So for ours, we had 4 digital inputs possible, and you can have 1 digital input controlling different shutters. So you can map it however you want. You can have up to 16 shutters with 4 digital input lines. So here are all the ASCII commands that we needed. I'll just have you take a look at one of them. You don't have to memorize them. Here, this is setting the state of the shutter, SST. Talk a little bit more about that later. Before I go into that, I'll talk about actually setting up and programming the Arduino. So of course we have an open source setup code in the GitHub here. And this is basically just to establish specifics. So this is the things that won't change. These are static, such as which shutter are we actually going to use. You can see up here, it asks, or we define either shutter servo or shutter solenoid, and you just uncomment the one that you want to use and comment the one that you don't want to use at the time. We also have to set up some more specifics like the address of the board and then the frequency. These are both default. Most of the time it works with the default settings unless you want to change anything around. So for the library and GUI, in case you don't want to remember all the ASCII commands, we included 2 libraries that basically do everything for you. Here's the example command I was talking about earlier, the SST. This is the serial port. This is through serial. And device number 0 is what we want to change. 1 means the state, it's open. 0 would mean closed. And then just a line termination code, which is needed for serial. But we also have the libraries. So in C++, this is the command here. And you basically give it the same inputs of the device number, which would be 0, and then the state, open or closed. And we have a library Python library as well, and it's the same exact thing where you give it the device number and the state. We also include GUIs, so these are 2 example GUIs. This is the Lab Windows, it's a C++ compiler, and this is we use mostly for troubleshooting, but you can do manually input whatever parameters you want. So you can give it which position is actually open, which one's actually closed. You can give it a manual position, get the device numbers, and yeah, all the commands are in here. Same thing for the Python GUI. This is through tkinter. These are just 2 examples. If you don't want to use Python or C, for example, MATLAB, you can do that. You just have to know the ASCII commands and then write it yourself. So for mounting, we also used CAD software to just basically create mounts so we could attach it to optical equipment. We 3D printed them, so it's just plastic PLA filament, which is very standard for 3D printers. And you can see in this first picture here, this is just the mounting of a servo. Second one is solenoid mounting, and of course you need screws and other things like this. And then the third here is just the 3D printed case of the touchscreen display. So this is our actual test setup. You can see on the right, it's not too complicated. The things we used were function generator, photodiode, an oscilloscope, and a laser. So we basically had a laser beam, and we had a lens to give us 3 different distances with the 3 different diameters. We used 1 millimeter diameter, 5 millimeter diameter, and 10 millimeter. And we basically just positioned the servo to test these out. And we had the laser beam go to the photodiode. So the photodiode would give a power signal to the oscilloscope. And then the function generator would give a signal to the shutter to open or close, and also a reference signal to the oscilloscope so we can check the timing. And then the shutters that we actually tested were 2 servo shutters, a small and a large servo, 2 solenoids, a linear and rotary, and of the linear we tried horizontal and vertical position, and these actually did change the results. And lastly, we did the commercial just for standard. Let's talk about the commercial first. So you can see this one is very fast. The x-axis is time in milliseconds, the y is power on the photodiode. And yeah, you can see it's very fast, and there's very little uncertainty, which you'll see a little bit later with the servos. And there's a picture on the bottom right. And if you'll notice the price, it's very expensive, so over $1,000 for this servo. Oh, sorry, shutter. And we have first the large servo in comparison, which obviously it's slower. We weren't trying to make it faster, just a more cost-effective version. And if you see all the colors and range, I'll highlight right here, This is an uncertainty because of pulse width modulation itself. Again, here's a diagram. Because the period is 20 milliseconds, you have always at least a delay of 1 period because it won't actually know which position to go to until the period is over, which is why you get the uncertainty. Same thing for the small servo, there's still uncertainty because it uses pulse width modulation, but this one's a bit faster because it has less inertia and it can travel faster. Our first solenoid is the horizontal that we tested, and we only did 1 millimeter and 5 millimeter because there wasn't enough throw to block the 10 millimeter beam completely. The delay for the horizontal solenoid, is larger, and we believe there's uncertainty. We're not 100% sure because of friction on the case. The closing is much faster though because of the spring load, and it just snaps into position. Again, we're not 100% sure on the uncertainty, but we think it's because of friction. On the vertically oriented solenoid, there is not much uncertainty because, again, we think the friction doesn't come into play in this orientation. And also gravity is helping us open because we have on the bottom the solenoid and it'll pull downwards to open. So gravity is actually helping us get a faster transit time. On the rotary solenoid that we tested, we were able to do 10 millimeter again because of the rotational motion, which provides more throw. It's also extremely fast too, but the con is that there's still the vibration of just solenoids because of the spring-loaded. Spring-loaded. Here's a graph of all of the tests. I'll highlight the middle one in a second, but we just wanted to give some recommendations. So the commercial one, of course, if you have $1,000 to spend and you need super precise timing, go for a commercial shutter. If you can sacrifice some of the timing, a small servo is the DIY that we did is much, much cheaper. And if you're okay with having some vibrations, if your experiment isn't too sensitive to it, you can go for the rotary solenoid, but the small servo is very quiet and has no vibration to it. And lastly, the results. Here are the actual numbers. So the commercial shutter is, of course, very fast. And then rotary solenoid is also comparable. But again, the vibration might not be good for experiments. And here's a small servo. So if you can sacrifice a little bit of timing, a couple milliseconds, a small servo would be your best bet. Finally, the cost estimate of our DIY shutter. With one servo, we had about $120 with everything that's required. So we need the Arduino Uno, we need a servo shield. You don't need a display, but for ours, we used a display, power source, servo, and other costs, yeah. So it was around $120. A 4 shutter system was around $140. Yeah, that was our cost estimate. So much, much cheaper than a standard commercial shutter. Yeah, that was it. I want to say that I didn't do this by myself. I had Professor Martin Fischer helping me. We used the labs in Duke University, and the project was funded by also the Chan Zuckerberg Initiative and the NSF grants. And I want to thank all of you guys for listening, and I'm happy to accept questions if anyone has any. And please check out the paper and GitHub. It has all the open source links.
Thank you very much, all of you, for joining, and especially for the presenters to make the time to be here today and prepare very nice presentations. This was fantastic.